Hello and welcome. In this video, we're going to be going over how to find higher order and trig derivatives. So we're going to start with a little warm-up proof here of finding the derivative of tangent. And we're going to be relying on our knowledge of ways to rewrite trig equations, particularly using their quotient to find these derivatives. So we're going to start by rewriting tangent is instead the derivative of sine over cosine, because tangent is equal to sine over cosine of x. And previously, we've talked about how to find the derivative of sine and cosine, and we also talked about how to find the derivatives of quotients, or things that are being divided. So if you recall from our previous lesson, whenever we're doing the quotient rule, we do the derivative of the first thing, which we consider to be the top of our equation. So the derivative of the top, the derivative of sine is equal to cosine of x, and we multiply that by the second thing, or the bottom of our equation. From that, we subtract the top times the derivative of the bottom. The derivative of cosine is going to be negative sine of x. And all of this gets divided by the denominator, or the bottom thing, squared. So in this case, cosine squared x. Before we do anything, let's go ahead and simplify our numerator. We could rewrite cosine of x times cosine of x as cosine squared x, and minus sine of x times negative sine of x becomes plus sine squared x, all divided by cosine squared x. Cosine squared and sine squared should seem familiar to you because that is a Pythagorean identity, which is equal to 1. So we have 1 over cosine squared x. Now 1 over cosine is the same as secant, so the final step is to rewrite this as secant squared of x, and that is what our derivative is equal to. So using just a little bit equation manipulation here, we're able to find the derivative of tangent. Similarly, we can do the same thing for our other trig functions. So for secant, cotangent, and cosecant. For homework, you are going to be showing the proof for these three. So go ahead, and if you want, you could pause this video now and give those a try, or you could come back to them later. Let's go ahead and take a look at our next example. Our next example is, how would we find an equation for the tangent, or the line that is tangent to the curve at the given point? So the curve in question is g of x equal to secant of x, and we want to find the tangent line when it goes through the point pi over 3, 2. So if we want to write the equation of a line, we need two things. We need a slope and we need a point. So to find our slope, we're going to go ahead and take our derivative. This is going to give us the instantaneous rate of change. Now, either above, or if you've already proved this, the derivative of secant of x is equal to secant of x times tangent of x. Now we want to go ahead and figure out what would the slope be for this specific point. So we're going to need to look at our x value. So in this case, we're interested in g prime of pi over 3. So we want to find secant of pi over 3 times tangent of pi over 3. Now if you're anything like me, you may forget certain values on your unit circle, so we're going to kind of go through this the long way. If you have them memorized, woo, more power to you. So secant we can rewrite as 1 over cosine of pi over 3. And tangent we could write as sine of pi over 3 over cosine of pi over 3. Now sine and cosine are two that I do always have memorized. So the cosine of pi over 3 is the same as 1/2. So this is 1 divided by 1/2 times the sine of pi over 3 is going to be root 3 over 2 over cosine of pi over 3 is once again 1/2. Now before I do anything here, I'm going to go ahead and get rid of this division by the fraction, which is the same as multiplying by the reciprocal. So this is the same as 1 times 2 over 1 times root 3 over 2 times 2 over 1. These 2's divide out, and we're left with 2 radical 3, and this represents, once again, our instantaneous rate of change, or our slope. This represents a slope because it came from our derivative function. So now we want to write the equation of our line. So we're going to be using our equation y equals m parentheses x minus h plus k. In this case, m is once again our slope, or 2 radical 3. Our h value was our x, so pi over 3, and our k value is our y, so plus 2. And we are all finished here. We have written an equation for our line. Remember, we don't always care about having it in slope-intercept form at this point. And those are kind of our trig derivatives. Now we're going to take a look at something called a higher order derivative. So a higher order essentially means what happens when you take the derivative more than one time. So we'll talk a lot about this in future units, but I wanted to do a little preview of it by thinking about its mathematical description and what it represents in real life. So when we're given a a mathematical function f of x, when you put an x value in, the output is a y value. We can think about this y value as a position. And for our real life example, I'm going to think of something that all of you are familiar with, which is driving in a car. And so if our function were to model how much your distance has changed over time, f of x would be how far you have driven, which is also another way of saying your position. How far did you go? How much did your position change? Now, when we've talked about our derivative, we've defined this as coming from our slope. It's our instantaneous rate of change. So our derivative, f prime of x, does represent a rate of change. Now, rate of change represents how quickly the position is changing. Now, if we think about this in our real life example, we think about our change in position or distance. So I'm going to use delta to represent change. Our change in distance over our change in time. You are probably more familiar with this as speed. So for instance, if you go 60 miles in 1 hour, your distance changed is 60 miles in that 1 hour. So this represents how fast you are going. You guys might be hearing my washing machine in the background there. Okay, so now what happens when we take a second derivative? So remember that derivatives just represent, it's a change, how much something is changing. And so in this case, if we're taking the derivative of our rate of change, it's going to represent how quickly our rate of change is changing. And if you've ever maybe taken physics, or maybe you have an inkling as to what this might represent, how quickly your rate of change is changing is going to represent how much you are accelerating or how much you're deaccelerating. So your acceleration. And if you think about this in terms of a real life example, think about this as merging onto a highway. When you merge onto the highway, you typically have to push your foot down harder so that you can speed up. And so this is how quickly we speed up or slow down. So if you think about this in terms of a car, the derivative is as though you are in cruise control. You are going a constant 60 miles per hour. Whereas the second derivative represents you speeding up or slowing down. So maybe you're merging onto the highway and you need to put your foot to the floor to speed up with traffic. Or maybe you are approaching a stoplight and you have to put your foot on the brake so that you can slow down. This is just an intro as to what these derivatives will mean and why we care about them. But for today, we're just going to be focusing on how do we find them. And so to find them, we just think about taking our derivative multiple times. So for instance, this is asking for the second derivative. So if we're given the function y, to find its first derivative y prime, in this case, we're going to apply the power rule. So that would give us negative 2 times our exponent 3 is negative 6 x to the, our power goes down by 1, so power of 2. If we multiply our coefficient, negative 4, by our exponent, negative 3, we get plus 12 x to the, our power is going to go down by 1, so negative 3 minus 1 is negative 4. Now for our second derivative, we want to know how quickly this is changing. So we would just take the derivative again. So negative 6 times 2 is negative 12x, and if I go down by 1, my power is going to be a 1. So I'm just going to leave it as 12x. If I do 12 times negative 4, that gives me minus 48 x to the, if I do negative 4 and I subtract 1, I get the negative 5th power. We could either leave this here. If we wanted to get rid of the negative exponent, we could rewrite this as minus 48 over x to the positive 5th power. Let's look at a couple more. I'd like you to try this one on your own. So find the first derivative. Once you've done that, make sure you check it in with me so I can see how you did. And we'll go to this last one and we'll do this one together. I would recommend pausing your video and trying 7 first. For number 8, it once again wants us to find the second derivative, so 2 derivatives. Now before we begin, we're going to rewrite y such that our exponent here is going to be, we won't have a root, instead we'll have an exponent. So the plus 2 stays the same. Our exponent becomes to the 2/5. Remember, a root creates a fractional exponent. Now we're going to go ahead and apply our power rule. For our first derivative, we're going to do our coefficient negative 1 times 2, which is negative 2. X, if I subtract 1 from my exponent, would give me a positive 1 power. So I'm just going to leave it there. For the next one, I'm doing 2 times 2/5. Now, if this is maybe uncomfortable, write it off to the side like that. That's going to give us plus 4/5 x. And I'm going to subtract 1 from 2/5. So 2/5 minus 1, or minus 5 over 5, is going to give us negative 3/5 for our power. Now they want the second derivative, so I'm going to do this one more time. If I take the derivative here, negative 2 times 1 is just negative 2, and our x is going to go away. And then I'm going to do 4/5 times negative 3/5. This is going to be minus 12 over 25, x to the negative 8/5 power. Once again, if I wanted, I could get rid of the negative or write this with the root. We're just going to go ahead and leave it here. We could also keep going and find the third derivatives, fourth derivatives, and so on, and we would just keep repeating this. So basically, when you want a higher order derivative, you just keep taking the derivative of what you previously had. I hope this video has helped you understand higher order derivatives and trig derivatives. Thank you so much for listening.